Okay, so let's get started with chapter 18 of the OSTEP book. So in the previous lecture, you learned what segmentation is. So segmentation is each segment of the process, like the code, heap, and stack, must be in contiguous memory, and the physical memory too. But they don't really have to. The the three segments don't have to be in the order that they were in the virtual memory, right? So so basically, sorry. So basically, let's say there's a code segment, then the content of the code, let's say, is this much. Then we cannot divide this to create to map the virtual memory to physical memory like this separately. But they need to be intact. Okay, the same for heap, stack, and all the same for all the segments. But of course, they don't have to be in the order like they did previously, where there was a heap right under code and then a stack and then space in between. You could just put stack here and then heap here. You could just do that. But the problem with this was that there could be external fragmentation, right? So that was the main problem. And over time, allocation becomes more challenging because even though there is enough space, right? Let's say there's some space here that's like 2k space in between this, that's like 3k. We want to put in a memory that's 4k, then it doesn't work, right? um so what we are trying to do now is, let's say we have a memory. This is the virtual memory with the code, with the heap, and with the stack. What we do is we divide this into equal let's say this, they look different, but we divide this into equal sizes, let's say 4k, 4 kilobytes, and then we save them to the physical memory, right? This is the method that just, to be honest, to me just made the most sense, because segmentation, I really, when I first learned segmentation, I was like, what the hell were they thinking? But segmentation is something that is just one method that was used historically, and later on we're going to learn segmentation and paging hybrid approach, where we use both segmentation and paging. It was used historically by Intel x86, so this book does cover it. But anyhow, so that's the first part, and this this uh, let me erase it and do it again. This division, right, it's called a page. This case, it's a 4 kilobyte page, and then it's pointed to page frames in the physical memory, right? So let me erase this. right? It's going to point to the physical memory, and the physical memory is also going to be divided into slots, 4 kilobyte slots, and these slots are called page frames. Now they put the term frame at the back, and for virtual memory they're just called page. These and then these pages are mapped, let's say something like this, to a page frame. Okay, so let's dive into 18.1. To help make this approach more clear, we will illustrate it with a simple example, which is this. It's a simple 64-bit address space, which means it's a virtual memory and it's 64-bit. And then the page is 16 kilobytes big, so it's page 0, 1, 2, 3. Okay. So that's it for this paragraph. And so the physical memory, as shown in figure 18.2, consists of a number of fixed size slots, 8 page frames, eight page frames, right? So it's 128 kilobytes. Oh, sorry, it's just byte. There's no kilo. I was so used to using kilo from the previous chapters. My mistake is just byte. So 128 byte physical memory, small memory. So these pages, they were mapped like so, right? And here's page 2 and here's page 3. Okay. And then of course in the physical memory, there must be space for the OS, reserved for the OS. So before, when we used to use stuff like segmentation and base and bounds, we needed to know we need to make assumptions about the direction the heap and stack grow and how they are used. But now we don't, that kind of thing doesn't really matter, because that's not the idea. The idea is we just divide the virtual memory and use it. So that's flexibility. And another advantage is the simplicity. It's actually really simple because there's just a free list of all the free pages for this. So for example, here we have free 1, 4, 6. And then it just grabs the free pages off from this list. I think there's an error here. For example, when the OS wishes to place our tiny 64-byte address space into our 8-page physical memory, It simply finds four free pages. Um, so this is not the thing that we're using. He's just saying, let's say we have a no, this is the thing, but they are saying they're assuming that this is unused, which is wrong because they said it's reserved for the OS. But if we do say it's unused, yes, and then there's indeed four free pages. The free list of all free pages for this is kept by the OS, and then just grabs the first four free pages of this list. Oh, I'm sorry. So basically, what they're saying is when they want to place this memory into a physical memory divided um, divided into 8 slots, 8 page frames, and of course this is reserved for the OS. It searches for four um, free pages, and the OS has the free list of all the free pages, and it grabs the first four free pages. In this example, the OS has placed virtual page 0 in physical frame 3. Yes, indeed. They put it here. Um, virtual page 1 on 7, page 2 on 5, and page 3 in frame 2. Yes, indeed. And 1, 4, and 6 are currently free, indeed. Okay, that's it. So to record where each virtual page of the address space is placed in physical memory, the operating system usually keeps a per process data structure known as a page table. So the page table, this is important, is kept per process. So it's kept per process address space. The major role of the page table is to store address translations for each of the virtual pages. Okay. It is important to remember that this page table is a per process data structure. An exception we'll touch on is the inverted page table. If another process were to run in our example above, the OS would have to manage a different page table for it, as its virtual pages obviously map to different physical pages. Modulo any sharing going on. So if there are shared physical pages, actually let's never mind. So now we know enough to perform an address translation example. Let's imagine the process with the tiny address space is performing a memory access. So what this does is this loads the data from the virtual address into the register EAX. And then we're just going to ignore whatever happened prior to this. So we're only going to care about this particular load instruction. So to translate this virtual address that the process generated, we have to first split it into two components, virtual page number and the offset within the page. So since there are 64 bytes, we need 6 bits total for our virtual address. So because 2 to the 6 is 64, so 6 digits, the binary digits are enough to address 64 addresses. So of course we start with 0 and end with 5. VA5 is the highest order bit, and VA0 is the lowest order bit. We know the page size, 16 bytes. Now 16 bytes, so each page has 16, which is 2 to the 4 addresses, 2 to the 4, which means 16 addresses can be represented by 4 digits. So that's the offset within the page. And then the page itself, so there's going to be 64 addresses, and then it's going to be divided into 16, 16, 16, 16, right? And obviously, because 64 divided by 16 is 4. Like, that's basically what division means at this point. And 4 pages can be shown by 2 digits, right? Because it's 2 to the 2. Um, well then, okay, that's what it's saying here. The calculations I just did is this paragraph here. Right, next is when a process generates a virtual address, the OS and hardware must combine to translate it into meaningful physical address. So let's assume the load above the virtual number here, or the virtual address here, was 21, right? Turning 21 into binary form, we get, yeah, 0101, because this is 2 to 0, 1, 2, 3, 4, 4 is 16, 4, 1. So add them all up and it becomes 21. Okay. And we can examine this virtual address and see how it breaks down. So we have a BPN at the first and the offset at the end. So what we can view from here is it's the first virtual page number, actually the second, but since the first is starts from 0, 0, so again we have the virtual page number like this, and then it's the second page number with the offset of 5, the fifth address of the second virtual page number. So indeed it's on the fifth of page 1. So we can now index our page table and find which physical frame virtual page 1 resides within. In the page table above the physical frame number, is 7. So what we see here is this is page 1, and before we saw the page 1 maps to page frame 7. It's frame 7. So the frame number is gonna be 111, which is 7. Now the frame number is also called the physical page number. But again, I like to use the term frame for physical memory and page for virtual memory. So I think I'm gonna stick to the term physical frame number. Okay. Note the offset stays the same because the offset just tells us which byte within the page we want. Our final physical address is this, and is exactly where we want our load to fetch data from. So that's going to be about um, so the half is how much? 120. So 117 is going to be about here, right? So that's where we get the address from. For the physical address, so the half is going to be I guess 24. So we want 21, so it's going to be about here. And 21 was right. Okay, with this basic overview in mind, we can now ask a few basic questions about paging. Where are these page tables stored? What are the typical contents of the page table? How big are the tables? Does paging make the system slow? Right, today we're going to do until chapter 18.2. And in the next lecture, I'm going to continue on I think we are gonna do several more lectures on this because it's not a small chapter. Maybe two or three more. Maybe I'll dedicate one lecture for each subsection. Maybe we'll do that. So page tables can get terribly large, much bigger than the small segment table or base bound pairs. I mean, base bound pairs are just, each process just has one pair, so it can be as large as the number of process, which is pretty small, to be honest. I mean, and the base bounds are like hardware registers. Um, so I mean, it's been a while since we've learned base and bounds, and I think it was chapter, what chapter was it? 16, I think. But like the base and bounds is interesting because that's where we started learning the core idea of address translation. That was the starting point of learning the virtualization of memory. Basically, virtualization of memory is address translation, right? And the point of base and bounds was each process had a certain starting point in the physical memory. So that's the base was um, added, um, and it was really fast because we just need to add the base and then compare if it is um, um, bigger than the bound. So it was really fast, but um, there were some problems. But if you look at the similarities of the two first, and then look at the problems that paging solves, the problems of base and bounds. Okay, so the similarity is that the OS still manages the free physical memory, right? With base and bounds, the OS tracks which physical regions are free. With paging, the OS tracks which physical frames are free by the free list, right? So it's kind of like base and bounds is, if you have physical memory, a big chunk, the process, the whole memory for the whole process is there, and then you need to look for places where we can put in this another process memory. So it's quite hard. But for paging, we have the physical memory, and then there are like pages in fixed sizes, right? So, I mean, this and this are the same size. They look different, but so you can put another page here. You can put another page here. There's not going to be any external fragmentation. Obviously, there's no external fragmentation in the base and bounds too. Um, um, because we have the assumption that the memory size is the same for all processes. If you recall, um, um, oh, so it was chapter 15 where we did base and bounds. But if you recall from the assumptions, we have the assumption that each address space is exactly the same size. That was the final assumption. But now with paging, we do not have to worry about that. If the each address space is not the same size, then there would be external fragmentation possible. It would be possible in base and bounds too. Anyway, and the third similarity they share is that the hardware still does the translation, not the software, right? So in base and bounds, the MMU adds the base register to the virtual address, and in paging, the MMU walks the page table. So the principle is that the hardware enforces translation transparently to the process, right? So the PC is just gonna look at the virtual memory, and then when it says fetch the instruction from the virtual memory, then at this point it changes to the physical memory, right? When they say when they look at an instruction and then it says fetch something from the virtual memory, then when it actually tries to load or store, it changes to the physical memory and does that. So all the all the actual fetch, load, store, all this ISA, instruction set architectures, all these stuff are done with hardware translation. And of course, the paging fixes a lot of the things from base and bounds. Like base and bounds requires um, physical memory, a contiguous physical memory. It's like a one giant segment with a single base and limit. Okay, then if the processes are not all in the same size, then there will be external fragmentation, as I told you before, just now. And then base and bounds um no has this large gap between the heap and stack, right? So that is like so paging only allocates frames for pages that actually exist. The gap, it just has no page table entries. So the 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 gap would not have a frame allocated for them because it is not in use, right? Um, Indeed, we're gonna learn more about that later on, right? In paging, the page table has an entry for every possible virtual page, but each entry has a valid bit. Each page table entry has a valid bit, and the pages in the gap simply have their valid bit set to 0, meaning this virtual page has no physical frame. So we're going to learn about the valid bit in later lectures. But anyway, so that's interesting to kind of come back to the base bounds pair and see how it compares to the paging, which is the last virtual memory technique, memory virtualization technique we're going to learn. So let's move on. So that was some long explanation right there. But so 32-bit address space with 4K pages. um Basically 32-bit address space is going to have 2 to the 33 addresses. And if there are 4 KB pages, 4 KB is 4 times 2 to the 10, which is 2 to the 12. So each page has 2 to the 12 addresses. So if you divide this by 2 to the 12, we get 2 to the 10. Oh, sorry, 2 to the 20. So there are 20-bit VPN, virtual page numbers, and a 12-bit offset. That's what this is trying to say. And the 20-bit VPN implies that there are 2 to the 20 translations. Now, 2 to the 20 is a big one. Now, of course, now, like I said, like we just seen before, the 2 to the 12 bits is an offset, so we do not need translation, right? Offsets stay the same, but the VPN must change to the PFN, which is the physical frame number, and there must be a mapping for each of that. So assuming we need 4 bytes per page table entry, right? The page table entry would map a VPN to the PFN. And let us assume the size of this is 4 bytes for now. So 2 to the 20 translations, 2 to the 20 page table entries, 4 bytes each, 4 megabytes. Right? Because 2 to the 20 is actually the definition for 1 mega. I mean, in some systems they use MB, but in this book they use mega for 2 to the 20. Anyway, so that's 4 megabytes, which is big. I mean, 4 megabytes is like what we use in the like a number that you would have seen. That means it's big. That's large. Now, if there are 100 processes running, then we need 400 megabytes of memory just for all those addresses translated. That's a big chunk of memory. Wait, so one thing that I have to point out is for each process, there's a virtual address space. We call it AES, starting from 0 to something. The thing is, 32 a bit up. Let's say we have a 32-bit address space 2 to the 32. 2 to the 32 is about 4 gigabytes, maybe. I'm not too sure because 2 to the 30 is a 1 giga, and then it's times 2 to the 2. Yes, so it's 4 gigabytes. So we're saying each processor has an address space of 4 gigabytes, and then they have they're gonna have virtual pages, and then we're going to have a page table for each of the processes address spaces, and they're gonna be mapped to the paid physical frames, right? And then um, so basically we need the page table needs to have a virtual um, um, page translation for all of the possible virtual pages, not only the virtual pages that are being used. So previously we talked about how the gap in between here, they don't actually have a, they're actually not actually allocated in the physical frame, but still they should have a page table entry for them because they can be potentially used. So the size of the page table has to be as big as the size of the virtual pages. Of course, we have to also multiply the size of each page table entry to the number of page table entries. Okay, so let's look at the aside. Oh, let me just finish this paragraph before doing the aside. So that's a large piece of memory just for translations. Um, when it comes to 64-bit address space, it gets even bigger, right? So let's do 64-bit address space. That is, I mean, that's huge, right? How, I mean, I don't even remember what this is. Um, anyway, um, a quick search tells me it's an exabyte. I've never seen a uh, I've never used an exabyte memory or disk in my life, so I didn't know. But 2 to the 60 is 1 E, and that's gonna make 2 to the 4 is 16, so that's gonna be 16 exabytes of 16 exa addresses, right? So 16 exa addresses, and then if we say we have like um 4 kilobyte pages, so that's gonna be 2 to the 64. 4 kilobytes was 2 to the 12, so that's gonna be 2 to the 52. 2 to the 50 is 1 petabyte, so that's gonna be 4 petabytes. 4 petas, 4 peta translations. And again, if we say we each is 4 bytes, then we have 16 petabytes. We need this much to store one page table, which is insane. So that's not realistic. Because page tables are so big, we don't keep any special on-chip hardware in the MMU to store the page table. Instead, we store the page table for each process in memory. Let's assume for now that the page table lives in physical memory. Later, we'll see that much of OS memory itself can be virtualized, and page tables can be stored in OS virtual memory. But we'll ignore it. Right, so here's a small page table. So the page table is, we have 3752. Okay, I don't think this paragraph is too important. So I think at this point we learned that paging is basically the perfect method for memory virtualization, but the problem is that page tables are way too big. There's way too much overhead. So now we are like, okay, then what should we do? So we're gonna start, I guess, a journey to know what to do. And the thing is, before we tackle the problem straight away, we just want to kind of start small. Okay, let's kind of forget how page tables are way too big and how we should shrink them. Let's first talk about what's actually in the page table. Okay, what's so here you can see a page table entry. What does it actually hold? And we can see some familiar faces like the page frame number, which should be at the top. And then there's some strange things at the back. So we're going to learn about these stuff, and then hopefully we can tackle the problem that we used to have, which is that they're too big. Um, and here we see how they can slow down things too. Um, we're gonna do some. You're gonna have to be aware. I'm gonna teach you all this in case you forgot them. And then they say we need two real problems: run too slowly, take up too much memory. And then we're going to do some exercise. And then the thing is, basically we don't solve the problem here. We just show you how the problems that it can have in chapter 18. And then we need to go to chapter 19 for faster stuff, and then chapter 20 for smaller tables. So there's a long way to go. There's a lot of lectures ahead. And then, of course, we have to solve the questions for each section to make sure we understand each section. So there's a long way to go. I hope to see you in the next lecture, where first we are going to look at each page table entry holds.